And also you have packages like NumPy and Pandas to have like cool data manipulation things, and also to do mathematical operations on arrays. And Google Collab, let me see. Okay. Now we have to move the mouse. Yeah. Oh no, it doesn't. Because it has. I have to.
Oh, I see. What if you just click on the screen?
Okay. Okay, let's see. No. Okay. Wait, what? Okay, good. Sorry about that. A lot of technical difficulties today. And Google Collab is one of the ways you can practice Python. Since usually you would have to download Jupyter Notebook onto your laptop, but Google Collab gives you an opportunity to do it on your browser instead of downloading things. Also, it gives you an opportunity to share it with your friends and like work on it together at the same time, just like Google Docs would allow you to share a text. Also, it allows to make easy text additions to explain what type of code you're doing on the like coding cells. So it's just a very easy introductory way to use Python. So I definitely recommend you to check it out. We have the link you can access to get like started with Google Collab. And then now let's move on to our main topics. So reinforced learning. Have you ever heard about this? It's fine if you never heard about reinforced learning. Okay. So it's a sub-branch of machine learning. And the main idea of it is to achieve an optimal solution for a problem using a sequence of unsupervised decisions. And that's really cool because we can solve problems, for example, how to play game really well and how to, so things like this, basically. Okay, so main reasons why it's used is because when you use supervised learning, you would have to, for example, for a game, you would have to have someone play the game, then you collect the data from how they play the game. And then you use that collected data to train your model. And but then you have a problem that the person would, your model will never beat the player you used to collect the data set. So that's where reinforced learning comes in. It doesn't require data to train your model, at least initial data. And then also it does not require supervision. So in the long run, it's possible that it will beat the human player playing against him. Real world applications of it, it really can be applied anywhere. It's mostly applied in training robots in game industry. Also, it's applied in financial industry, for example, in market making. It's applied in natural languages, healthcare, news recommendations, and many, many other things. So when you start playing around with reinforced learning, you can apply it in any sphere of your life. And now let's look at how exactly does reinforced learning work. So it's in the beginning, it would be similar to supervised learning. So we have a framework, same as in supervised learning, and then we create some neural network model, which we run through our framework and get some sort of output. However, opposite of supervised learning, we don't have a target label on the output action which we get. So in the supervised learning, for example, if we have two possible actions up and down in the game, we would know which type of action we have to get based on the data set we used to train our models. However, in the reinforced learning, we wouldn't know what action we should take in this particular situation, since we don't have the data set we're training our model on. And that's the main point of it, that we can use our policy network, and that's how we call the neural network we use in reinforced learning to get the action. The easiest example of policy network is policy gradients. And the main idea of it is we take some random network and which creates a random action. And then we check, does it achieve our goal or does it go against our goal? And if it goes against our goal, then we create some sort of punishment for the system, so it knows that it achieved the wrong thing. And if it achieves our goal, it gets a treat. It's very similar to how we train our dogs to do things. So it's a very simple idea. And we can use also random distribution between the actions. So we make sure that the action doesn't repeat itself. So our model tries different ways. One time it goes up, one time it goes down, and it's a combination of different things. And of course, while our training and while we're collecting the data, so when those actions lead us to achieve our goal, and when our actions lead us to lose, we usually lose it at first because our model is not trained enough. It doesn't know what it's supposed to do. But over time, more times we run it, better our problems get, our model gets. It pretty much learns similar to how humans learn to some extent. And it also filters out the negative, the sequence of actions which leads us to negative reward, and it amplifies the amount of actions which lead us to positive reward. So over time, it's supposed to make our model to be as optimal as it can get. But the problem with the gradient policy, which we looked at, is that what if our initial random neural network doesn't lead us to our desired goal? What if the problem ahead of us is too complicated? So it's not only like going up and down, but what if there is some sort of other circumstances? And then we will never win. So our model will be stuck. It will go again and again, but it cannot learn. So that's why very smart people came up with reward shaping algorithms. But their main problem, which is also their main advantage, is that they're customly done for each single problem we have to solve. And that can create initial problems. It can actually achieve our desired goal in unconventional ways. For example, if our goal is to jump as high as we can, it can actually make and if our constraint on the winning is the distance between the ground and the bottom of our feet, it can make like a flip where the difference will be very big between the bottom of our feet and the ground, but then it wouldn't actually jump. It would just count the distance rather than jump higher and higher each time. And this is problems which can have to be addressed for each single example we are working on. And it's really hard to create an optimal algorithm And that's why this approach might be not the best each single time. So there is a lot to work in regards to this, and it's really fun. So if you like complicated algorithms, I definitely recommend you looking into reinforced learning. And also similar to, oh no. No. Okay, you're a genius. Yeah, and of course, similar to other machine learning things, it has some ethical problems since it allows us to train robots. It has potential to increase unemployment, and since it also leans towards teaching our artificial intelligence to make decisions by itself, it can be used badly in the hands of like monopolies, or if the government decides to do mass surveillance, or for weapon technologies, it can also be very tricky. And our only hope is that international law will develop fast enough to address all those concerns and help us address them before they become a big international problem. So, moving on. Any questions?
I guess I have one. I was gonna ask, like, what are some ways to like combat some of the ethical scenarios, considering like the unemployment one is like a very like true one happening now? Is there like ways that can be helpful instead of, I don't know. I'm just, that's like my one thing that I've always been like stressed about with AI is like taking so many jobs away.
I think that it can be actually reversed, that yes, it takes jobs away, but it also creates the jobs, because there should be people who train AI, who work with it, and who work on creating it. So if we educate people and train them to work on AI, they can actually fulfill those jobs, because there is a lot of demand and not that many professionals who can work in the area. So in my opinion, that's one of the ways which can be addressed. Yeah.
Also, like value alignment. How do you make sure that the artificial intelligence is like aligned with what people want? Because like I think we're regularly just like it's like a thought experiment where like you're having like an AI just doing paper clips for you, and then at some point it just transforms the entire world into like making factory because the rewards didn't line up right. So how do you like connect that?
That's actually one of the biggest challenges which are inside of a reward shaping idea, that if we create like a customized rewards for each single problem we have in front of us, how do we make sure that the algorithm we create is addressing the problem we're trying to solve and doesn't overstep the boundaries? And that's what like the greatest minds in the industry are trying to address right now. And hopefully in the future, no one will make some fundamental mistakes. So what we can do is, study hard, and hopefully we can be the ones who solve it. Yeah.
Not really a question, but there isn't somebody to make the game based off of that again. It's called Universal Paper Clips. I highly recommend it. It is terrifying. It starts out as it's like a text-based incremental game, except then obviously like you start enslaving the human population.
Oh my God. You came prepared.
I will look at this so-called game.
All right. Next section.
I was gonna say, since we do have this topic,
Yeah, I'm gonna cut out actually the first slide. This is a demo. It's pretty cool. I'm definitely happy to talk about it after the presentation. For now, for the sake of time, we'll skip on to the main stuff. So this section is about generative adversarial networks. what are they? It's kind of in the name. They are networks that are both generative and adversarial. But in case you need just a little bit more, by generative, we mean that these are networks that are creating new instances of data. So you might have heard about neural networks in the past that classify data. For example, a network that you can feed images into, and it'll tell you if it's a cat or a dog. You might have also heard about neural networks that predict based on existing data. So networks where you can feed in a house size and location, and it spits out the house price. This is a new type of network where it's creating entirely new images or audio or any other type of data. And then the second keyword is adversarial. And that means that there are two neural networks that are actually pitted against each other. So the networks work in opposition, and that's how they both improve. So a little bit more on this idea of having two different neural networks. So one of the networks is called the generator, and the generator takes in random input and then produces these new data instances. And then the second network is called the discriminator. And the discriminator looks at real data that you provide and the generated data, and it tries to determine what's real and what's fake. So the discriminator is rewarded for successfully detecting the fake data that's produced by the generator. And the generator is rewarded for successfully tricking the discriminator by producing results that the discriminator thinks are real. So you can see how they're kind of working against each other. So the basic idea is that over time, the discriminator gets better and better at detecting a fake image versus a real image. And the generator gets better and better at producing realistic data. So by the end, if the generator is able to trick the discriminator, that basically means the generator would be able to trick a human too. And that's exactly what we want. So let's look at an example. Let's say for some totally legal and legitimate reason, we wanted to get really good at creating fake money. And so we decided to do that with a GAN. So when we start out, our generator might produce something like this as a $10 bill. Doesn't look very realistic. And so we would take that and we would feed in a real image of a $10 bill, and we would put that into our discriminator, and our discriminator would very easily be able to tell us the one on the left is the fake one. So then we go through training after maybe like 50 or 100 iterations, we might get something like this, where like, yes, you can kind of tell it's a $10 bill, still doesn't look really convincing. You can definitely tell, and the discriminator can tell too, which one is the real one and which one is the fake one. But then once we've done enough training, we might finally end up with something like this. And this, when you feed in the image on the left, the discriminator classifies that as real, even though we know it's fake. And that's how you would know that your model is successful and ready to be used in the real world. So what are some use cases for GANs? Pretty much like Nora was saying, GANs can be used all across the map, just like reinforcement learning. So some popular use cases are image reconstruction, which you can see on the top left. So you feed in an image that has some data removed for some reason, and it kind of like comes up with what the original might have looked like. In the middle, you can see art style transfer. So you feed in an image and it tells you what that would look like if it was painted by Monet or Van Gogh or some other art style. On the bottom, you can see that GANs are used in the medical field for drug discovery. GANs are also used in the media. If you've heard of deepfakes, that's all done with GANs. And it's not just for images, GANs can create music, which you can see in the bottom left there. So GANs are really useful. That does not mean that they're easy to work with. There are a lot of technical challenges. One big one is non-convergence, which basically happens when the parameters are oscillating and they never set on a defined value. So if you think about it, we're trying to find the optimal values that create the best possible generator and the best possible discriminator. But if no like best possible values exist, then we can't train our model as intended. Another common technical challenge is mode collapse, which is where the generator only learns a specific subset of the input data. So if we think about our money example, let's say we were trying to generate $1, $5, and $10 bills, but our generator only learned to produce $1 bills, then it might successfully trick our discriminator, but it's still not working the way we intended. And then another issue happens when the discriminator and generator are imbalanced. So if our discriminator gets really, really good really quickly, then it's not going to be tricked no matter what our generator does. So our generator won't learn, and then we can't train it. Aside from all the technical challenges, there are also some pretty clear ethical concerns. One of them is product farming. If you go back in the slides and look at our demo, what we do is create an image just like on the spot based on some keywords. And that means that anyone who has the right GAN or access to a GAN can create artwork and sell it as their own, which could really affect artists who spend hours producing a single piece of work and make a living from that. And then there are obvious issues with deepfakes as well. If you can create a realistic video of literally anyone doing or saying anything, that could have massive implications in politics and beyond. Okay, so any questions about GANs? Yeah.
Well, I'm gonna really be discriminative in that, because if it's really good, then if the generator can take or it can do it good or good enough, then wouldn't that be really good?
That is a great question. So we do want our discriminator to be really good. The issue is if it gets there really quickly. And so like going back to the money example, you can see there's a clear difference between the top and the bottom, right? And any of us would say the bottom one is better, at least you're getting closer. But if the discriminator gives the same feedback for both of those, then the generator doesn't know whether it's getting better or worse. So it can't improve over time. Does that make sense?
Yeah.
Any other questions?
I don't have to be like separately like trained on some data set because they essentially start off as like completely that.
Yeah, did you want to add on to that, or did you have another
It's not
question?
a question.
Oh, okay. That is a really good question. That gets a little mathematically complicated, but we can definitely talk about it after, because it does, I do understand how it looks confusing that it gets random input and then produces a sample. But I don't know if we have time to go into it right now. Yes.
So if like the generator doesn't know like which one's better or something, because then why don't we like switch to like not a binary fake or real system? Why don't we just say like, oh, this is 1% good and this is like 5%.
So that is what it is if you go into the math. Like if you got in specific, I do think it runs it through a function that spits out a probability of it being real versus a probability of it being fake. But yeah, for like the sake of simplification, it just says real or fake. Any other questions? Okay, cool. Okay.
And really quick to change it, you just click.
I was using arrows. That works for me, but
Okay, cool. All right, everyone. So we're on to our last topic, recommendation engines. Does anyone have any examples of what they think a recommendation engine might be? If we think of where recommendations pop up as we go through the internet. An idea? It's definitely similar. They can be involved, but when we get into it, recommendation engines are things like Netflix, YouTube, Amazon. Basically, they're systems that try to predict whether a user will like an item. Here we have products for Amazon, movies for Netflix, YouTube spits out videos at you. In these systems, we use machine learning in two places, both in collecting data on our user. Here are a couple things that we might look at, like user history or the behavior of similar users. And we also use machine learning in mathematically describing our users and products in a way that allows us to actually generate predictions. To look at that idea of mathematically describing our users and items based on their traits, we're going to look at one-dimensional embedding. 1D embedding is a technique where we put our users on the bottom and our items, in this case movies, on a line, dividing them up by some trait. Here, whether they're like child-oriented or adult-oriented, and for the users, just sort of their preferences for either. The user placements will generate from looking at the stuff from before, past likes, how similar users liked each movie, things of that sort. Well, item placements, at least for movies, are done by a mix of manual placement by content experts, actual people at Netflix who say this movie should be like these genres. And also usually the content producers will give like a list of genres with their movie. This might be more complicated if we have something like Amazon. We would need a separate machine learning model to read the product description, figure out what it's actually for. And when I'm, go to the next slide.
Put on the screen.
Oh, too far. Okay. So let's extend that idea up to another dimension. In two-dimensional embedding, we create a graph or a matrix of two different traits now: blockbuster, art house, children, adult. These are our two axes. And basically, since I have it in person, we create user and item vectors of these traits. A user vector would be a straight line from the origin to our user. Well, a item vector would be origin to item. And then we take something called the dot product, which is essentially a measure of how those two vectors overlap. So this here and this here, kind of like that. They've got a fair amount of overlap. So we could see that Harry Potter might be a pretty good fit for our user here. So yeah, the dot product is essentially a measure of similarity between like a user's tastes and a movie's genres. More positive dot product, the better. Let's say, just hypothetical example, we have a new user. We might start them off at the origin where we know nothing about their tastes. So we're gonna give them random movies or just like whatever's popular. Then they watch Shrek, as you do. That would move them up and to the left a bit. And from there, we now have some data that we can generate recommendations on. We can take the dot product of our user in their current position with every other movie, and we could see that besides Shrek, which they already watched, Harry Potter would probably be the most similar thing based on taking that dot product. Let's see here. So yeah, it might seem like honestly AI isn't super involved in that process, but how far our users should be moved after watching Shrek, and how far or like how shifted that user's recommendations would be by how similar users acted, those all have AI kind of behind the scenes in them. So we have two main ways that we decide on recommendations. We have content-based filtering, which is essentially where we look at this user, they watched these movies in the past, they hit like on this stuff, let's generate recommendations based off of those. And collaborative filtering, which is like, this user mostly watched horror movies. What do other people who mostly like horror movies, or what do they enjoy? And we generate our recommendations off of that. So this data can be both explicit or implicit, because if they hit like on something, dislike on something, that's a very clear signal. But let's say they watched 10 episodes of this in one night, even though we aren't explicitly like, okay, they like it, we can probably infer some sort of just like information about their preferences. So at the heart of collaborative filtering, the idea of dot products on the vectors I mentioned before, we can do that not only between users and items, but between two users, just sort of measuring the overlap of their tastes. So if we see that Alice and Bob both watched Fast and the Furious, and then Alice watched Death Race, by collaborative filtering, we might say they have similar tastes, let's recommend that same movie to Bob. But if we go into content-based filtering, let's say Bob, every violent movie he's ever watched has had a thumbs down. So we might rethink recommending him to watch Death Race. So it's kind of these two ideas or like methods of generating recommendations that we have to both take into account. So there are some issues with recommendation engines as we handle more types of data and just more data overall. The first would be sparse data. This is essentially that we or most users generally have near zero preferences, likes on most topics. For example, if you think of your own like Netflix history, you're probably only within a couple genres. There are definitely things you haven't touched. And how is our system going to create like good recommendations or any recommendations at all if they have near zero data to work with on the vast majority of things? The second is scalability, because if we are handling every product on Amazon, every video on YouTube, that is simply just a lot of data. How do we fit that on a laptop? We probably can't fit it on a single server. We would need some kind of like distributed server network if we're trying to host the entirety of Amazon. And of course, like all our other AI topics, there are still ethical considerations with recommendation engines, even if they seem less malicious than deadly robots. Because if you think of something like Amazon, this is hypothetical, but they could do something like, say, just nudge some values. Okay, Amazon Basics products will always be higher up in like the rankings, the listings for products. That'll drive more user interaction, more products sold, basically more money. So something like that could give like the creators or anyone with potential influence just an ability to sort of make the system somewhat unfair. The second is that if you've ever spent any time on YouTube, you might have heard creators talk about something called the algorithm. This is basically how it can feel almost random, how on YouTube, creators might get more watch time some months, less watch time some other months. They might get a random spike in subscribers, anything like that, and how it can be kind of random feeling, like if nothing changed in their own content. This randomness though makes like relying on YouTube or things like it inherently unstable of like a livelihood, because you're kind of just reliant that YouTube is going to keep recommending your stuff, even though sometimes it does, sometimes it doesn't. This makes it really hard for a lot of people to like feel secure in things like this as a career. And that can just have like real world consequences, because AI are not perfect. Recommendation engines aren't perfect. Sometimes it's going to mess up. It's going to give a bad recommendation, but stuff like that can have real impacts if you like sell stuff on Amazon or create content on YouTube. So I know, oh, there we go. But yeah, so with this section, we have a Collab notebook that we mentioned before. If you guys want to walk through like a simple example of a like little movie recommendation system, you can say like, give me movies like Toy Story, and it'll spit out, okay, here's Toy Story 2, here's Ants, all of these things. Yeah, so I know I rushed a little bit, and next slide is just questions. I'll leave this here so you guys can see the link. But while we have a couple minutes left, does anyone have any questions about our topic? Or does anyone want to revisit slides? I know they were pretty quick. All right. Okay.
Okay, so I do just want to say thank you for coming. Thank you for bearing through the technical and room difficulties we had. But real quick before the conclusion, can we just give a round of applause for all our presenters? They did such an amazing job answering questions and presenting content when the setup is not ideal. But yes, so please do fill out the feedback form. I wrote it on the whiteboard and also sent it on the chat for those of you joining us on Zoom. And it's also linked in the slides so that we can, make improvements and also continue to hold like events like this in the future. Shameless plug, please do follow us on Instagram and Facebook to, be in tune with other events that we're going to have in the future. And if you had any questions, feel free to also email us. Do you think you can enter the email in the chat? And we'll share the email with y'all too. But yeah, if this piqued your interest and you do want to learn more about AI, we do offer other tracks/workshops. So we have a beginner track workshop happening on Thursday, 6 p.m. to 8 p.m. this quarter. But if you can't make that time, we do have past workshops that have been recorded and posted on the ACM YouTube channel. And also, if you're interested in more of the non-technical side of things, we do have like ethics courses that we collaborated with ACM Teach UCLA on, and the website for that is linked on the slides. So with that, I think that's pretty much it. I'm going to stop sharing the screen.